Imagine trying to build an intricate origami box, but you are only allowed to open your eyes for a split second every 10 seconds.
Oh, that sounds completely impossible.
Right, you would have absolutely zero sense of physical momentum. You wouldn't know how fast your hands were moving or, how the paper was bending between glimpses.
Yeah, you'd just be guessing at that point.
Exactly. And that is precisely the handicap we give to today's most advanced robots when we use static vision language models to control them. So, welcome to AI Paper Podcasts. Today, we are doing a deep dive into a really fascinating paper called ViVa, a video-generative value model for robot reinforcement learning.
Yeah, published by researchers at Giga AI, Sichuan University, and Tsinghua University.
Now, for those of you pulling material for a short-form edit, here's the one-minute summary of the key insights. The core problem in embodied AI right now is that vision language action models, or VLAs, really struggle in the real world due to delayed feedback.
They just don't have that temporal awareness.
Right. So reinforcement learning relies on a value function to assess task progress. But current VLM-based value functions fail because they only understand static snapshots. They completely miss the temporal dynamics.
They see the what, but not the how.
Exactly. So the solution the authors propose is ViVa, a video-generative value model. They essentially repurposed a pre-trained video diffusion transformer, specifically 1.2.2, to predict the future instead of just classifying the present.
Which is such a clever use of a generative model.
It really is. By taking current multi-view images and a 14-dimensional robot proprioception vector as input, ViVa jointly predicts the robot's future proprioception alongside a scalar value representing task progress.
And the results are just massive.
Huge. Integrated into the RVCap reinforcement learning pipeline, ViVa hit a 73% success rate in real-world box assembly. That completely crushes the VLM baseline of 58%, while actually being faster to train and run inference on.
Yeah, that efficiency piece is wild. But to really understand why moving from static images to video generation is such a fundamental paradigm shift for robotics, we really need to look at how advantage estimation actually works within a framework like RKPay.
Right, because continuous control tasks are incredibly messy.
Exactly. A robot operates under severe partial observability and heavily delayed feedback. Like, if an agent is assembling that cardboard box, it might make a tiny microscopic error on fold number 2.
But the structural failure isn't even visually obvious until fold number 10.
Precisely. The RL pipeline requires a multitask value function to constantly evaluate the current state and determine if the current policy is on a trajectory toward success or failure.
And recently, state-of-the-art architectures have leaned really heavily on vision language models for this evaluator role. They essentially frame value prediction as a classification problem.
Right, just asking the VLM to look at the camera feed and assign a score based on, semantic visual alignment.
Which exposes a massive architectural blind spot.
A huge one. VLMs are trained on static image-text pairs. They are unparalleled at semantic understanding. They know exactly what a cardboard box is, and they can easily identify a robotic gripper.
But they lack any foundational prior for kinematics.
Exactly. They don't model spatial evolution, momentum, or physical causality. When a VLM looks at a frame of a gripper moving toward a box, it only registers spatial proximity.
It has no mechanism to compute whether that gripper is approaching at a safe, controlled velocity, or if it's about to violently punch right through the cardboard.
Yes. Using a VLM to estimate RL value is sort of like trying to predict if a basketball team will score based on a single photograph of the player's mid-jump.
I love that analogy. You can identify who has the ball, sure, but you can't see the velocity of the pass. You can't see the trajectory of the defense reacting. You really need the full video to understand the causal chain of events.
And this brings us to the paper's core insight. Value estimation in robotics is not a classification problem. It is inherently a problem of anticipating the future.
Right. The only way to truly know the value of a current physical state is to accurately simulate how the future will unfold from that exact state.
Therefore, video-generative models, which are explicitly optimized through massive data sets to capture spatiotemporal evolution, they are really the only logical foundation for an embodied value function.
Okay. But if value is just anticipating the future, how do you actually build a model that does that without training a bespoke physics engine from scratch?
Well, you hijack an existing one.
Exactly. The architecture here relies on repurposing 1.2.2, which is a state-of-the-art diffusion transformer. But they didn't fundamentally alter its core transformer blocks.
No, they used a technique called latent injection to force it to process robotic telemetry.
So they take the 3 multi-view camera feeds and compress them using the model's pre-trained spatiotemporal variational autoencoder. That handles the raw pixel data, converting it into a dense latent space.
But then they have to feed in the proprioception, right? That's a 14-dimensional vector containing the end effector pose and all the joint angles.
And to do this, they use something called repeat padding. They eventually take that tiny 1x14 vector and tile refeed it until it mathematically matches the massive spatial dimensions of a visual latent frame.
Which sounds a bit crazy at first.
It does. I mean, hang on. If you take just 14 numbers and repeat them thousands of times to fill an entire latent frame, doesn't that massively skew the attention mechanism? You're basically flooding a visual model with a tidal wave of redundant kinematic data.
You would intuitively expect catastrophic interference for sure, but this really highlights the sheer adaptability of transformer self-attention.
Oh, wow. So it just figures it out.
It does. When you project that highly redundant tile-repeated vector into the latent space alongside the camera feeds, the attention heads quickly learn to process it not as a spatial patch containing textures, but as a dense global conditioning signal.
So the cross-attention layers use that proprioceptive latent to globally contextualize the visual patches.
Exactly. The model learns to fuse the mathematical state of the arm seamlessly with the spatial geometry derived from the cameras.
And for the actual value output, they use a reverse trick called the broadcast method. They take the target scalar value for the task progress and set every single element of the final output latent frame to that exact same normalized number.
Right. It creates this uniform, solid color latent frame where the intensity of the color represents the likelihood of success.
And the training process ties all of this together using a flow matching objective.
Yeah, and unlike standard diffusion models that often learn to predict raw noise, flow matching regresses the vector field that optimally transports the simple noise distribution directly to the complex data distribution.
So the model is given a sequence of clean conditioning frames, a zero initialized blank token, the current proprioception latent we just discussed, and the 3 current image latents.
And its objective is to take pure noise and denoise it directly into the target frames, the future proprioception at a specific time horizon, and that uniform scalar value frame.
Okay, so we have successfully tricked the video-generative model into acting as a physics simulator by disguising joint angles and math as latent pixels.
Basically, yes.
But a physical simulation is useless to an RL pipeline if the robot doesn't know whether that simulated future is actually good or bad. How do you mathematically define success for a model that thinks in pixels?
Well, the paper defines the stepwise reward algebraically, but audio is a terrible medium for equations.
Yeah, let's visualize this as a progress bar instead.
That is a much more intuitive way to frame it. For any successful episode, imagine a progress bar counting down to 0. Every single step the robot takes toward completing the task shaves a tiny fraction off the total cumulative return.
So the entire trajectory of a successful operation maps cleanly to the numerical range between 0 and 1.
Exactly. As the physical task nears completion, the scalar value drops closer and closer to absolute 0.
But a robotic environment is highly volatile. What if the robot perfectly executes 99% of a box assembly, but gets its gripper caught on the final flap and rips the cardboard?
Which happens all the time in the real world.
Right. Visually, the entire trajectory looked like a success right up until the final moment.
And this is where the author's discriminative supervision signal proves its worth. If an episode fails at any point, the final step reward is instantly flipped to a value of 1.
Oh, wow.
Yeah, this instantly adds a full integer to the cumulative return for that entire specific trajectory. It shifts the value of that failed attempt entirely into the range between 1 and 2.
Creating a mathematical, uncrossable boundary of exactly 1.0. The model never has to navigate a blurry semantic middle ground where it wonders if a visually messy success is actually a failure.
Exactly. If the value is 0.99, you are definitively on the path to success.
And if it evaluates to 1.01, the policy is doomed. This rigid margin must provide an incredibly clear, unambiguous supervision signal when the flow matching objective is denoising that value latent frame.
It completely resolves the ambiguity between slow progress and outright failure. But, to prove that this architecture is actually learning physical causality rather than just exploiting statistical shortcuts, the authors ran a series of really revealing ablation studies.
Oh, the ablations in this paper are fantastic.
Yeah.
The most critical one asks a simple question: does predicting the future actually matter?
Right. They compared the full ViVa model against a stripped-down version that was trained only to predict the scalar value, completely ignoring the future proprioception.
And when they removed the requirement to predict future joint angles, The model basically became blind to suboptimal robot actions.
It did. During a physical box assembly trial, the robot made an anomalous movement, like a clear mechanical mistake. The stripped-down model's value estimate barely registered the error.
Because it kept assuming everything was fine since the static visual scene still looked roughly like a box.
Exactly. But the full ViVa model showed sharp, immediate drops in value precisely when those anomalous physical events occurred.
By forcing the model to explicitly simulate the physics of its own arm, it cannot just rely on the visual aesthetics of the task. It has to deeply understand the underlying mechanics.
Which leads directly to their second ablation regarding the prediction horizon, represented by the variable k. They needed to determine exactly how far into the future the model should simulate to get the most accurate value estimate.
And they found that k equals 50 steps is the optimal window. But why does the performance break down if you push the horizon to, say, k equals 100? Is the future just inherently too chaotic to predict? Or is there a specific architectural bottleneck happening in the model?
It is a fundamental issue with how transformer attention degrades over extended horizons and continuous control environments.
Because the physical world is highly stochastic.
Right. When you attempt to predict 100 steps ahead, the variance of possible futures just explodes. The self-attention mechanism becomes saturated as it tries to assign weights to wildly divergent, highly probable future states.
So this uncertainty waters down the gradient for the value function, making the signal really noisy and weak.
Exactly. And conversely, a horizon of k equals 10 is too short. The model becomes hyper-reactive to transient visual noise without understanding the broader kinematic trajectory.
So k equals 50 hits that causal sweet spot where the physics are predictable enough to provide a strong gradient, but far enough out to prove genuine temporal understanding.
And we see this temporal understanding clearly in the third ablation, which directly compared the video backbone against the VLM baseline during a shirt folding task.
Yes, the graph for this is so telling. The VLM's value estimates fluctuate erratically, just bouncing up and down based on shifting shadows or changing wrinkles.
ViVa, however, produced a steady upward progression. You can observe clear, definitive spikes in value precisely at key physical milestones, such as the exact moment a sleeve gets tucked or a fold is completed.
It is a perfect visualization of the core thesis. The VLM is easily distracted by visual noise, but the video-generative model understands the causal sequence required to manipulate the environment.
Right. The theory is sound, and the ablations prove the mechanics. But let's look at the real-world deployment, because a model that only works in a sterile simulator is pretty useless to engineers.
So true. They deployed ViVa on 3 highly complex real-world tasks: shirt folding, box packaging, and a remarkably difficult toilet paper organization task.
Oh, that toilet paper benchmark is a phenomenal test of fine motor control and temporal reasoning.
It is so complex. The robot must grasp a flexible, easily torn material, tear off a single sheet, discard it into a bin, collaboratively use both arms to rewind the remaining loose end until it is flush with the roll, and finally apply a sealing sticker to secure it.
All within a strict 300-second time limit.
While the paper focuses its quantitative deep dive on the box assembly, the qualitative difference in a task like this is striking. The VLM baseline struggles immensely with the temporal coordination of flexible materials.
It just cannot perceive the building tension of the paper or the necessary momentum for the dual-arm rewind. It gets totally lost in the visual homogeneity of white paper.
But ViVa, because it actively predicts its own future joint angles and the resulting environmental physics, successfully anticipates the physical tear point and seamlessly coordinates the rewind mechanism.
And when we look at the hard numbers for the box assembly task, the performance gap is undeniable. Running the RECAP pipeline with the standard VLM baseline yielded a 58% success rate, with a throughput of roughly 11 completed boxes per hour.
When they simply swapped the value function to ViVa, the success rate jumped to 73% and throughput increased to 14 boxes per hour.
That is a massive leap in policy optimization. The paper also highlights that ViVa generalized significantly better to novel, unseen objects, whereas the VLM's performance degraded sharply the moment the visual distribution shifted.
And here is the efficiency surprise that completely defies conventional wisdom. When you hear diffusion transformer and video generation, the immediate assumption is massive computational overhead and crippling latency.
Oh, absolutely. But ViVa is significantly cheaper to operate than the VLM baseline.
It's wild. ViVa required only 4 GPU days to train, compared to 6 GPU days for the VLM. And for inference, ViVa takes just 0.18 seconds per step, while the VLM lags behind at 0.32 seconds.
This really comes down to architectural efficiency and sequence lengths. Large language models, when adapted for vision, operate autoregressively.
Right. They often require flattening images into thousands of discrete tokens, which then have to be processed through dozens of massive attention layers.
And because transformer attention scales quadratically with sequence length, this is computationally brutal. ViVa circumvents this entirely. By utilizing the VAE for latent injection, it compresses the multi-view images and the proprioception into just a handful of dense spatiotemporal latent frames.
So the diffusion transformer is operating on a radically shorter sequence, achieving deep physical reasoning without the crippling bloat of LLM tokenization.
It is a brilliant piece of engineering that honestly redefines how we should be utilizing foundational models in robotics.
ViVa conclusively proves that generative video models are not just tools for creating synthetic media or fun clips. They are highly efficient, powerful physical world models capable of evaluating complex, temporally extended interactions.
They can look at a chaotic scene, accurately simulate the kinematics of what happens next, and provide a mathematically rigorous evaluation of a robot's current policy.
Ultimately, it represents the necessary evolution from static pattern recognition to dynamic causal modeling. If we expect autonomous agents to operate reliably in a dynamic, continuous world, their internal evaluation mechanisms must be natively capable of simulating that dynamism.
I couldn't agree more.
Which leaves us with a final provocative thought for you to consider. If predicting the physical future is the ultimate test of understanding current value, if forcing a model to simulate physics is what it actually takes to evaluate a real-world scene, will the next generation of foundational AI models have to incorporate video generation at their core just to acquire a basic common-sense understanding of cause and effect?
That is a fascinating question.
Think about what that means for the trajectory of artificial general intelligence. If an architecture cannot simulate the physics of the future, perhaps it can never truly understand the state of the present. We will leave you with that. Thanks for joining us on this deep dive.